I'm ready. All right, can you see the slides?
Yes.
Yes, very good. So today I'm going to present about LSTM networks for named entity recognition. My advisor is Professor Iren Valova. So as you can notice, the topic is very closely related to the topic that Andrea Heinz presented. So there will be some overlap in the presentation. But I'd like to point out that my work has been done completely independently from Andrea's. First, I'd like to give an outline of my talk. I'll introduce the notion of the named entity, and we'll discuss what is the named entity recognition problem and why we need to worry about it. We'll talk about the neural network architectures that are suitable for that type of work and for sequence analysis. I'll present a couple of data sets that we use for testing. Next, we'll examine the parameter tuning findings so that we were able to fine-tune our model on one of the data sets. And then I'll show the cross-validation results that we obtained on both of these data sets, and we'll compare different architectures and different type of LSTM cell performance. And finally, I'll show some results, and we'll have a discussion and conclusions. So I'll introduce the named entity recognition problem based on the following sentence. Steve McQueen provided a thrilling motorcycle chase in these greatest of all World War II prison escape movies. So what are the named entities? So a named entity is a real world object that can be denoted with a proper name, such as people, places, organizations, good, etc. And the example of the data is given on the right-hand side. We can see that sentence in our table in the first column. And then we can see the labels that call the named entity recognition tags giving in the second column on the right-hand side. And the first two words are defined as an actor. So it's given a label of actor. Then there are labels O, which means that's basically does not belong to any of the named entities. And then we see that the rest of it belongs to the plot, opinion, and the plot again. So why do we need this to be able to define the named entity recognition, which became a new subfield of natural language processing field of studies? Well, it's an important pre-processing step for information extraction, information retrieval, and other natural language or text processing applications. For example, if we worry about the document information retrieval and we have the NER tags, then information can be searched much more accurately than if we do it in a raw text. So how would we analyze the sequences, which are our sentences? A standard approach is to use recurrent neural networks that are shown on this slide on the right-hand side. The special feature of the recurrent neural network is that it can provide the state from the previously processed step to the next step, and therefore the information that came from a text, for example, before current word, can influence the interpretation of the present instance. And that architecture is quite successful for speech recognition, language modeling, time series in general. However, it has one shortcoming. It works well if the gap between the relevant information and the place where it's needed is small. So RNN can learn this information effectively and provide a good result. But as the gap widens, as we see on this slide at the bottom, RNN becomes less effective and it's unable to learn and pass the useful information. It gets lost over several input or several time instances. So that's a problem for a natural text processing because we might have to deal with longer sentences, and the effect of the beginning of the sentence might affect interpretation of all the words in a sentence. So people overcame this problem by inventing a very special type of RNN cell and much more complex architecture than a standard cell. And these cells are called overall long short-term memory cell. And these cells has the ability to remove or add information to the cell state and actually retain this information for a long time. And the cell state, you can see a pipeline that goes all the way through the cell, and it can actually retain information as long as necessary. The cell can also, using the forget gate, can forget some information that is no longer needed and can add information that is relevant in the current context. So that cell state regulated, as I mentioned, by 3 gates, forget, input, and output gates, and that successfully overcomes the gap problem it can remember for a long time. There are other types of cells that people invented. For example, one of commonly used cell is the gated recurrent unit cell that is shown on the right-hand side. So the advantages of this cell, that it's a simpler cell that has fewer parameters, but it provides a lot of the functionality that a standard LSTM cell can offer. And the difference is that it, for example, combines the forget and the input gates and then merges the cell state and the hidden state. So we'll try both of these cells, see which one works better and which one we should use for our task. So the architectures that we considered was first the standard bidirectional LSTM cell shown on the left-hand side. So why do we need a bidirectional network is because in a language processing task, not only the effect of words before the current word might affect the outcome, but also something that comes perhaps at the end of the sentence might be important. Therefore, we pass through the data in the forward direction and in the backward direction. And this way we get the optimal interpretation and tagging. But what also we tried is two stacked layers of bidirectional LSTM cells, because the deep bidirectional LSTM we thought might be worth a try. Sometimes these deep networks are beneficial in natural language processing. So these are two data sets that we worked with. One of them consisted of food reviews and another one was movie reviews. The food reviews contained more than 7,600 sentences and it had 3,800 unique words and also 17 NER named entity recognition tags. An example of this data set is shown in this table. And movie reviews contained close to 10,000 sentences, but it had many more unique words, over 12,000, and also contained 25 NAR tags. And the example is shown on the right-hand side. And also I'd like to say that movie reviews had longer sentences overall, so that was a more challenging data set for our models. So let's review quickly the data pre-processing for the LSTM network, for the LSTM networks. So the data comes as a CSV file, as we have seen with two columns. Then I split this data into individual sentences and combine it with tags, as we show at this step. Then I create dictionaries. So we name each unique word as a number, assign a unique number, and we assign unique number to each unique tag. And in this case, you can see 17 NAR tags that are all numbered. After that, we need to prepare our sentences, our corpus of data to supply to the LSTM networks. The network should take the input of the uniform size. Therefore, I'm padding the sentences to the size which I decide is optimum for this data set. For example, if I look at the distribution of sentence lengths, I can see that 25, for example, is about as long as it gets. So I set it at 25, and I pad each sentence, which is shorter than 25, with some kind of end fill as shown here. And then I can send it into the embedding layer, which creates a dense representation with a certain output dimension, which I choose, and we'll talk about it later. So our parameter tuning findings are shown on this slide. The first parameter always to worry about is the number of LSTM units, and close to 100 units were achieved accuracy as probably as high as it gets, but then as we increase the number of units, the accuracy does not improve. So there is no point to complicate our model beyond the 128 units. Also, we report three numbers. The loss and accuracy come from TensorFlow, and these are basically the numbers that we obtain on padded sentences, so the standard length. But what we're really interested in is the accuracy without the end padding, which is typically well identified. So I cut the end padding, and then I recompute the accuracy, which is slightly less, but that's the number we need. So over 88% we achieve in this case. I studied the size of embedding layer, and what we see is that close to 50 dimension provide again optimum accuracy. There is no point in this case to increase much more than 50 dimension because it slows down, complicates the training, but the accuracy is more or less the same. And the dropout rate was not actually affecting very much the accuracy of our results. I left it at 0.1, so I have some regularization in the model. And the model was the optimum number of epochs to feed the data was equal to 10. And beyond that, the model showed a clear overfitting behavior. So let's look at the cross-validation results where we compare the performance of two types of cells, the standard LSTM and the GRU-based cells with single bidirectional layer. And you can see we use the 10-fold and 5-fold cross-validation in this case. And the interesting result is that gated recurrent unit networks consistently provided somewhat higher accuracy compared to LSTM networks for the case of 5-fold or 10-fold cross-validation results. The next table shows the comparison of LSTM and GRU-based networks for two stacked bidirectional layers, something we call the deep network. And in this case, the accuracy is still good, but it's not better than the accuracy we achieved with a single layer. So for our data sets, there is no point of complicating the model and going into the two stacked layers. A single bidirectional layer is optimum. So the last parameter we investigated is the maximum sentence length. In this case, it's the second data set where the sentences can be almost as large as 48 words. So we set the parameter to 30, 40, and 50 words in a sentence. And we can see that the accuracy of padded sentences actually increases with the sentence length, as we would expect, because our padding is well identified, well classified. But the accuracy with end padding remove actually stays the same, which is good. It means that our model is not strongly dependent on this parameter, and we get values which probably are unaffected by the choice of this parameter. Again, if we look at the GRU-based network versus LSTM network for the same maximum sentence length, GRU-based network provides somewhat better performance in terms of total accuracy. So let's look also at the confusion matrix for one of the data sets. It's for the movie reviews, the bigger data set. Overall, we achieved the accuracy close to 86%. So most of the values are on the diagonal. So the outliers highlighted in yellow, as a number of outliers, they all belong to the class O, which is not a named entity. So it's a very diverse class. So it's not surprising some mislabeling happens for that type of tag. Another type of tag where we notice stronger mislabeling is when we see mislabeling of I plot labeled as a B plot. Obviously, there is a strong crosstalk between these closely related labels. It's not surprising. Also, B plot gets mislabeled as I plot. That's also not surprising. This label, which is I opinion, gets mislabeled as I plot. And why it happens is it's because there is just not enough. There are not enough instances of this label. So this class is not well trained because of the low support of this tag in the data. So let's look at some other performance matrices for the food recipe data sets. You can see precision recall F1 score classified for each tag. They all, in fact, have pretty decent values, 70, 80%, except one tag, which is the I price tag. And again, in this case, the support is low. There are only 76 instances of this tag in the data. So pretty clear that as long as we have enough data in the training set, we can identify our tags pretty well. And the overall accuracy is 89% in this case. And this is the movie reviews data set. I would say the conclusions are similar. For example, for B actor tag, which has a lot of support, 1,500 instances, we get the F1 score of 92%. And for instances that are like I soundtrack, we get only 0.25 F1 score because there are only 41 instances. So it's really related to how well the class is represented in the data, but overall accuracy is still very decent, 85%. So to conclude, the bidirectional LSTM networks enable the named entity recognition task, so we can clearly see we can achieve that. We developed a Python code based on TensorFlow 2 library that provides framework to actually use different types of LSTM cells and test different network architectures, so a versatile tool. After hyperparameter tuning, we achieved good accuracy between 85–89% on the test data sets. And the accuracy of our tagging was pretty strongly dependent on the prevalence in the training data, which is not surprising. GRU-based networks achieved somewhat better performance compared to the standard LSTM cell-based networks, and stacking 2 layers of bidirectional LSTM networks did not provide any further improvement. Thank you, and I'm happy to answer your questions.
I second the call for questions. We have a minute and a half approximately. Please go ahead.
I just have one question. In the parameter tuning findings, you have this number of LSTM units and also number of layers. Sorry. you notice that when you increase that to be more units and more layers, the accuracy drops. Do you have an insight why this happens?
Well, I wouldn't say the accuracy drops. I would say it stays more or less the same. I mean, we're talking about the third digit after the dot, right? So it's not, I mean, I wouldn't consider that drops, because if we look at the standard error, let's look at the standard error that I obtain when I compute cross-validation results. I mean, you cannot really talk about the third digit after the dot. I mean, it's these numbers are effectively the same. So that's
okay. So it means this is like the best thing can get. So it cannot get better with more units, right?
Correct. There's just
okay.
There's only so much you can get out of this. Having these data sets, complicating model further is just not gaining any more accuracy.
Okay, thank you. I got it.
Thank you. Any further questions, please?
Yeah, I have a question actually on this slide too. Sorry if you mentioned this, but I missed it. But did you also consider like possible correlations between parameters? So for example, I guess my intuition might be that as the units increases, the need for dropout may also increase to kind of regularize. So is that something to consider or that you looked into?
Right, so I haven't looked into that, but I have exactly the same thought. That's why I kept the 0.1 dropout at 0.1, because that I suspect if I remove it, it will get worse because it will start overfitting. That's right.
Okay, great. Another question is just kind of about the transfer of architectures. So I guess you looked at a food data set and a movie one. Can architectures tuned for one data set continue to perform well after retraining in another data set, and just generalize any other kinds of data sets that you may also throw at it? So like, do these generalize pretty well, or would you have to retune them from scratch?
So I would say on these two data sets, they generalized well. In fact, we conducted study of what is the, for example, the optimum number of epochs and optimum number of units. And that was the same for both data sets. These are, for example, epochs number coming out of TensorFlow, and I have the same picture for another data set. They all had the peak close to 10 epochs. These data sets are similar enough, but I would say if the data set would be much bigger, I would actually expect difference in the performance, because at the end, a standard LSTM cell has more parameters by approximately 25%. And with sufficiently large data, it should perform better than the GRU unit. So I would say yes. If we increase the amount of data substantially, then I would say I would recheck the number of parameters, because these two data sets are more or less comparable, and that's why I generalized well in these cases.
Great, thanks so much for the talk.
Thank you. I'm going to stop the questions here because we're already over time. Thank you to the presenter.